Okay, so in the last section for today, we're going to be covering the concept of clipping. Well, the concept and application of clipping for a rasterizer. So this is a very crucial part of any fully fledged rasterizer. So the idea here, as you can see, is if we have a screen, there will come times when primitives don't fall exactly on the screen or off the screen completely. So they might straddle the screen, and in those cases we do need to clip them or make sure that we only draw the portion of them that actually intersects the screen. So we're going to cover doing this for points, for lines, and for triangles. Okay. Now, you might have something where you might think that this is already taken care of if you have like an X or a Y check in your rasterizer when you're plotting a pixel. And that can catch certain circumstances, especially in 2 dimensions. However, as you might imagine, if you have a very large triangle and only the tip of it is on screen, and you're generating all those pixels for that entire triangle and rejecting 99% of them, well, that's not exactly the most efficient way to go about things. So we're going to talk about some ways to clip items so we'll actually be able to draw just those items that are on screen. That's a big part of clipping for efficiency. So let's go into this, and we'll of course start with the easiest one to talk about, which is points. So 3D points, when you're clipping them, it's fairly straightforward, as you might imagine. You probably have something already in place that can handle most of this. So one good space to do your clipping in general is NDC, or normalized device coordinates. Remember, this is our range of -1 to +1, +1 to -1, 0, 0 being in the center. Very nice to clip in because these limits are fixed and they're known regardless what the resolution might be. So NDC is a good space to do clipping in. There are some caveats to that, as you'll see, but overall it's a solid space. You can wait till screen space too, where you have XY coordinates in terms of pixels, and you probably already have some of this, so that you can do that there too, and we'll have applications for that too. But one thing you need to also concern yourself with now is not only could one of these points be off to the left or off to the right, above or below, but it could be too close or too far as well. So for our 3D point, you'd also want to test for your near and your far plane values. All right. So you can just check the Z for that component. You can check the Z value in NDC and see if that is below 0. Remember, because in NDC 0 is where our near plane is, in NDC anyway, and or above 1, 1 being beyond the far plane in NDC. There is one thing to watch out for, though. And this doesn't really have to do with points, but something we'll have to think about moving forward. When you have a point with a negative Z value, when you do, and when I mean a negative Z value in projection space, or let's say view space, then projection space, if you have this starting negative Z value, once it's in view space, this can be a problem. Because remember, our Z ends up in our W, our view space Z value becomes our W value. And if that's negative, remember, you're dividing things by that value. So if you have a -1 and you have some positive X and positive Y, you can cause the sign to flip on those X and Y values when you do the perspective divide. And while that doesn't seem like a big deal for 3D points, right? That doesn't seem that big a deal because, well, if it's behind the camera, or sorry, if it's behind the near plane, who cares if it flips? That might be your thought process. Like, well, who cares? I can't see it anyway. Well, you're right about points, but here's the major issue when you do stuff other than points. When you try to do lines and triangles, when the x and y flip on part of those lines or triangles, and this is only for triangles and lines that straddle the zero plane. So the line is partway visible and partway completely hidden behind zero. When that one flips, like this diagram here shows, suddenly the line looks completely different. Like it's the shape of the line has changed because the end point behind the zero plane is actually in a new location. So once we go to draw it, it actually draws differently than it should. And that's a huge problem. So if you wait till NDC when you're dealing with lines or triangles, and those lines or triangles happen to cross the zero boundary or the zero plane, yeah, you're going to have some interesting visual problems that occur. So that's troublesome. That's something we have to consider with. So as we've talked about here so far, points, not really a problem. But if you look at what points do when they're behind zero or they're less than zero on the z, it has some repercussions for points that are connected to other points. So how do we get around this? That's what we need to talk about next, because we want to avoid this orange line, how it's been changed from what it originally was after it's been divided for perspective. That's a problem. We want to avoid that. As you might imagine, it would also affect triangles, because triangles, after all, are 3 lines. All right, so clipping 3D lines. We need to talk about this. How can we deal with this now that we are aware of this problem? Problem is NDC is just too late, right? If we let things go to NDC, then the shapes will already have been, lines and triangles will already have been permanently changed. We don't have to worry about triangles or lines that are completely in front of the near plane or completely behind the near plane, because we can just throw those away and not worry about them, because they'll either work fine if they're all in front, they'll just work as normal, or if they're completely behind, we'll just throw them away because we're not going to draw them anyway. But it's the ones that are in the middle, that are across that zero plane, those are the ones we have to worry about. Okay, so here's a solution. Why not do the clipping before the perspective divide? So if we do this before we do the divide by W, then we don't have to worry about the XY signs flipping on the vertices that are less than 0. So you don't have to worry about that. But this does seem daunting. That's the only problem. And I'll tell you why it's daunting. Because when we were in NDC, everything was nice and simple. It was like, well, where's the left-hand side of the screen? -1. Where's the right-hand side of the screen? +1. The top, +1. The bottom, -1. Easy peasy. What about near you and away from you? 0 and 1. Super easy. Not anything to concern yourself with. So NDC is super nice for clipping. So when you go before NDC, when you go into, like, say, world space or view space or projection space, well, where's the left-hand side? Where's the right-hand side? We could probably define those with as planes, but the problem with those planes is they're no longer nice and easy and convenient values of just of a simple x and a y. Especially if we talk about, let's say, world space. Now the plane itself, we have to define it with a normal. We have to define it maybe with vertices that represent the extents of the frustum in world space, which could have any given orientation. It becomes a lot more complicated to deal with. But I got some good news for you. We can, if we think carefully about this, we can simplify this problem quite a bit. Take a note about this. Homogeneous projection space, that is the space right before we convert to NDC, right before the space that we actually divide by the W, projection space. View space values, so those values that are near the near plane, they've been actually shifted to 0. So if you actually go back to day 4 and look at the end when we start doing the matrix math, you'll see that what happens is with the Z transformations, you actually end up shifting all of the values. So items that were around the near plane, like let's say our value of the near plane is 2, and you have a vertex that is at 2.1. Well, something that the projection matrix will do is it will take those Z values and they will bring the 2.1 to 0.1. So it'll move everything as if the near plane was at 0. So this is really important to note because that's really nice. That means homogeneous projection space is essentially the same as far as the near plane goes as NDC space. They're both at 0. So everything else is different, like the planes, and the far plane is, of course, the near minus, it's actually the value of near minus far in projection space, but it's not 1. So everything else is quite a bit different here. But at least 0 in homogeneous projection space is still the near plane. And if you moved it to view space, then the near plane, of course, would be the near plane, and then our situation would be 2. So it's nice that it's 0 in homogeneous projection space. What this means the point of this, anyway, the point of this is that if you do clipping against the near plane, it's very easy in projection space, because you know where that is, and it's not some strange plane in 3D space. It's just a Z of 0 is the near plane. That's where the near plane is. So anything below 0 is clipping or cutting into the near plane. So it's going through it. So here's the trick that we can use. Not a trick, but here's some useful thing that we can do. Here's the thing. If we cut our lines and triangles, in this case we're doing lines, well, it'll also help us with triangles, but if we cut our lines along the near plane, so if we chop them so they start from the near plane, if they are intersecting the near plane, we basically get rid of the portion that is passing through. Then if we are able to somehow do that, if we are able to do that, and then we do the perspective divide, well, guess what? Now we don't have to worry about having these XY values flip sign on us, because we no longer have Z values that are negative. So this is really powerful, because we don't have to worry about that anymore. So if we can just cut our lines here on the near plane, then we can do our clipping in NDC, because that means we can safely move into NDC without having to worry about this weird behavior that we talked about earlier, this flipping of signs. As long as we can have non-negative Z values, then our NDC perspective divide to go into NDC will not cause any problems. So this is our goal. Cut lines on the near plane, and then moving into NDC shouldn't be a problem. So how do we do that? How do we actually cut a line on the near plane? Well, of course, first thing is you have to have your line in projection space. So that means before you bring it into NDC, before you do the perspective divide, you have to have it before that point. After is too late, so it's got to be before. And it's actually really simple if you remember your parametric line equation. Okay, really simple. Remember how parametric works? You take a change on one axis against the change of the total amount along the line, and that gives you a ratio. It works for X, it works for Y, and guess what? It also works for z. So all we have to do is, if we know that one vertex of the line is crossing the z boundary, if one vertex of the line, if its z is negative, like in this case that would be a here, well then if we just take the absolute value of a or flip the sign of a, whatever its negative value is, say it's negative 3, say it's positive 3, well it's 3 pixels, or not 3 pixels, but 3 units too far into the screen. It's coming 3 units too close. If we compare that against the total change in the line along the z, let's say this edge is, like I said, negative 3 from 0, that's our total change of 3, and then same deal here if the rest of the way is 6, so if this total distance, if this is 6 and this is 3, then we have a total distance of 9. And if we, like I said, if we take the absolute value of this change and we take the absolute value of whatever this difference is across the entire thing, then we're going to get 3 over 9, 1/3, 0.3 repeating. So we are 0.3 repeating too far beyond the near plane. So this is really handy because if you have this ratio, well, if you remember your parametric line equation, if you know the ratio, you can solve the point on the line, on the true line, exactly. So we can solve point C here if we solve the ratio. And here's the formula to do that right here, C being a vertex. So by dividing the two deltas, you get your ratio. You can then place your ratio into your standard linear interpolation formula, and you can interpolate from A to B the ratio amount ending up at C. So this is pretty powerful. This actually allows us to intersect the line right on the near plane. So that's pretty cool. Keep in mind though, when we're doing this linear interpolation, what we're trying to create is a new vertex, And remember, vertex is more than x, y, z, w. You could also have color, UV, etc. etc. So that's important. So not only you have to interpolate the position, also interpolate any attributes. Because remember that C is going to be a brand new vertex, so it has to have appropriate values for whatever other attributes are attached to that vertex as well. So make sure you interpolate all of those things. All of those things need to be interpolated by this 0.3 repeating that we found. But really, that's it. So that's pretty cool. We can just using the parametric equation, we just chop the line right on the near plane. And as we were talking about earlier, once we do this, now it's safe to move into NDC. Now it's safe to do our perspective divide because we no longer have to worry about vertices that have a negative z that will flip signs on our x's and our y's. So that's very handy. So here is highlighting even more. So let's say we've taken our line, we've clipped it, and now we have a line that, although it is chopped on the near plane, it still does not perfectly fit into the boundary of the screen. But here's the great news. We can use the same exact technique, but instead of doing it with the near plane at 0 on the z, we can now clip against the NDC's x, y, x's and y's against the different planes. We have 4 planes here to chop against. We have the positive x plane, the negative x plane, the positive y plane, and the negative y plane. And we can just take all our vertices, see if our line is straddling any of these planes, and then chop appropriately based on the distances traveled. So the same concept applies in 2D just as well as it did for when we're chopping against the near plane. So pretty powerful stuff here, pretty useful. And you can see it's essentially the same formula from the last slide, just on different sets of axes. And of course, instead of 0, right, instead of comparing the deltas from 0, we're looking at these extent boundaries of our screen in NDC. Pretty neat. Now I do have a recommendation for you, and that is try to check if your lines are completely inside or outside of the boundary before doing this work, right? Because it's kind of pointless to put in this work to cut these lines apart if you know you're just going to draw the line because it's completely on the screen, or you're just never going to draw the line because it's not on the screen at all. So the big question, right, is like, well, how do I know if it's on the screen or not on the screen at all? Well, it's pretty easy to do these sorts of checks. Because if you think about it, all these vertices and indices, they have x's and y's, right, for this 2D space. And if you look at, say, the x and y here, and the x and y here, well, if both of these y's are greater than +1, then there's no way it could be on the screen, right? But at the same time, if both of those y's, in this example down here, if both of the y's are less than -1, there's also no way it could be on the screen. Same is true for x's. If both of the x's are greater, if both are greater than +1, no way. If they're both less than -1, also no way. So those are quick ways to make sure that, that you can completely reject a line if it does not, if there's no purpose in drawing it whatsoever. So that's a nice thing, fast, quick thing you can do before going into this and cutting your lines apart. Just make sure that they have any purpose to be drawn in the first place. All right. So now that we've talked about lines, and now we've covered points, we've covered lines, now it's time to talk about how do we handle triangles. Now triangles, of course, would seem like this would be the most difficult one of all, and there is some logic involved, but here's the good news. We can really apply the things we've already talked about, that line cutting, to help deal with these triangles. Because after all, remember, these triangles, A, B, C, these 3 vertices that make up the triangles, we can break those apart into 3 separate lines. And if we remember that, then it'll make this process a lot easier. Because we can find, if we find where lines intersect, multiple lines intersect, we essentially find where the triangle intersects. All right, once again, I recommend using plane tests like we just talked about, like with the lines. If both of the x's are less than 1 or what have you, then you can fully accept or reject triangles. For the beginning, though, to do 3D triangles, we do have to concern ourselves. Before we concern ourselves with the 2D portion, we have to concern ourselves with triangles which may be penetrating the near plane. Okay, it's triangles that we're too close to, that are coming too close. So once again, their z values could be causing problems if they're negative. So we have to cut them on the near plane, just like we did lines. So easy test to do initially is, are all 3 points of the triangle greater than the near plane? Are they greater than 0? Well, you don't have to worry about chopping it. Are they all 3 less than 0? Well, you'll never see it anyway, so just get rid of it. So those are quick, easy tests you can do right off the bat. So, as it says, just like 3D lines, got to first clip our triangles to the near plane before we can worry about 2D plotting. Also, this has to be done, once again, in homogeneous projection space. Because, once again, if we wait till the perspective divide, it's way too late. It's the same thing we talked about earlier. So just to remind you, if we have these vertices and they're negative, and then we divide by W, too late. Things will mess up. All right, so when we are going to do this with triangles, when we're going to cut our triangles along the near plane, there's 2 key scenarios that are going to happen. There's 2 situations you have to deal with when they have to be cut. So let's talk about those 2 scenarios. So here's the first scenario, and that is interpolating from the hidden edge. So this is in this situation, one of the lines that comprise the triangle is hidden. That means 2 of the vertices have z's that are negative, that we cannot see because they're below the near plane. So that is problematic. So one of the ways, this is actually the easier of the two scenarios to deal with, because you can just take those two vertices that are hidden and intersect them with the near plane. So you can see here A is being intersected to IA, C is being intersected to IC. You can use the exact same method that's used here, well, more particular here because it's the Z, but you can use this exact same method. In fact, if you wrote the function well enough, you can just use the same function to cut those edges along the near plane, and that'll give you your intersecting point. So in this case, our C will be one of the new corners of the new triangle. So here you can see them. Pretty straightforward. And then you just draw the triangle as per normal, but you using the newly modified vertices. Now keep in mind, it's not always going to be this diagram you see here, right? It's not always going to be A and C are behind or B is in front. It could be the exact same situation we need, but it could be C in front and A and B behind, or A in front and C and B behind. So there's a couple combinations you have to be on the lookout for. But really the key thing here is there is a hidden line. There is two vertices that are have negative Z values. That's to identify this situation. All right. So yeah, this one's not too bad. Once again, don't forget, vertices have things like colors and UVs. Gotta interpolate those too. So don't forget about that. All right. You might be wondering what these diagrams are of. So let's just be clear on what these are here. While I'm changing colors, think about what space do these diagrams represent? Can you figure out what space they are? Look at this one. 0 is where the frustum ends, and then there's a near and a far plane, and the near plane is not equal to 0. Well, can't be NDC, right? Because NDC, 0 is where the near plane is. Can't be projection space either, because as we talked about, in homogeneous projection space, 0 also means the near plane because everything's been shifted. So this definitely isn't world space, because the camera wouldn't be, 0, 0 wouldn't be the tip of the frustum. Definitely not local space, so that's way too early, and we don't have any idea of like where the screen is or anything at that point, nor in world space for that matter either. So that means that only leaves one space. This must be U space. Yep. So this diagram of U space, this one right here, you can see 0 is where our near plane is. So this is definitely not U space. You might think, oh, is this NDC? Well, remember, I said that if we clipped in NDC, it would be too late. So this isn't NDC. This is not view either. So this is homogeneous projection space, or just projection space for short. So this is our pre-W divide space, our projection space, after we've multiplied things by the projection matrix. Okay. So this one should be self-explanatory. You should know what this one is just by looking at it, right? It's NDC. And as you might have guessed, well, what's this one? Well, if we're doing more clipping, yes, this is projection space. Homogeneous projection space, but I like to use projection space for short. Homogeneous is implied. So yeah, here in projection space, just like with lines, you need to clip things. So just kind of trying to cement what these diagrams are meaning, what spaces we're talking about when we're looking at these. Okay, so this is our first scenario with triangles: clipping the hidden edge, interpolating to the actual visible vertex. So we're going to interpolate to the visible vertex. So you can probably guess what the other situation is, right? The other situation is you don't have a hidden edge, you have a visible edge. Now this one is a little trickier, as you can see, because when you have a visible edge and then you interpolate to the visible edge, you actually end up with a quadrilateral, right? You end up with a shape that has 4 points, and the problem is you can't, if you were to wanted to draw that shape, those 4 points, you have to write a new type of drawing routine to draw quadrilaterals. And let's just not do that. Let's take an easier approach. Well, I think it's easier, but a more effective, not more often effective approach and a more efficient approach. And in fact, this is what 3D hardware does as well. Let's just take that quadrilateral and split it into 2 triangles. And then we can just draw the 2 triangles instead. So this is a method of dealing with this situation. So it's a little bit more complicated logically because you have to split the quadrilateral, but is essentially the same thing as before. So let's take a look at this one. So instead of taking the 2 vertices and interpolating to the opposite edge, essentially you're going to take the single vertex, the hidden vertex, you're going to duplicate it or copy it. In this case, you see I've taken B, I copied it into D as well, and I've taken that same point, and then we interpolate those 2 points across so they intersect the near plane. And once again, this is the same technique as before that we used for the lines and in the prior case. And here you can see I have ID and IB. The I stands for interpolation. So you have an interpolated D and an interpolated B. And then we are going to end up with 4 points, A, IB, C, ID. And then we're going to take those 4 points and split them up so we get 2 triangles instead of 1 quadrilateral. So really, we only have 1 new extra point here, right? So that's all you really need to do is when you're returning, like let's say you're returning new points, all you really need to do here is return, instead of returning just 3 points for your triangle, you return 4, and the 4th may or may not be a new vertex that you need, depending whether you're in this situation or in that situation. So that's just kind of a recommendation on maybe how you might set up your function that does your clipping or whatnot. In all cases, I recommend you return like an integer that says what happened. For instance, 0 could mean that don't draw this triangle at all because it's completely behind the near plane. 1 could mean, oh, you better draw this triangle completely. It's fine. Don't mess with it. It's completely in front of the near plane, so you don't have to clip it. And then maybe 2 could mean, hey, it intersected and I cut it, and here you go. Here it is. I cut it into a smaller triangle for you. And then 3 could mean, yeah, I did what I did in 2. I cut it up, but I actually have 2 triangles now, not just 1. So you might want to set your code up in that way, so you know exactly what happened inside that function. But yeah, so you have to write a little extra logic to see what to do when you have this 4th case. But once again, it's not too hard to detect in any case, because in this situation you have 2 vertices that are visible and you have 1 that's hidden, as opposed to in the prior case you had 1 that's visible and 2 that were hidden. So not terribly hard to detect these situations. All right, one thing that's kind of helpful, it really won't affect you too much for today's lab, but if you want to have a full-fledged rasterizer that works much like hardware does, you will want to try to keep the original winding order of the triangle. Like for instance, this original triangle is wound in a clockwise fashion. A, B, C. See how it follows a clockwise order as opposed to if C and B were switched, it would be a counterclockwise order. Not generally, but ideally, you're going to want your triangles that come out of this clipping to also follow those rules. And depending on which vertices are in front or behind the near plane, you might have to take some, you might have to make some logic splits on that based on what happens. For instance, if A is behind the near plane, it might have a different impact as if C was behind the near plane, and so on and so forth. All right, so all of this, once again, once you do this, now you have triangles that are guaranteed to be safe to put into NDC because you no longer have any vertices that are negative on the Z. So this is the same deal as we had with the lines. Very useful. So once we have a triangle, once we have these purple triangles that we know are in front of the near plane, they're not necessarily guaranteed to fit onto NDC. So once we do the W divide, they could still look like this. They could still be beyond the range of our NDC ranges. Remember, this is our positive 1, negative 1, positive 1, negative 1. It's our NDC, of course. And you have triangles here that don't completely fit. But here's the good news. This part is super easy, especially if you did the brute triangle algorithm. Because remember, the brute triangle algorithm already builds an axis-aligned bounding box that lets you do a double for loop so you can only search the area of the triangle. Well, all you have to do to make that algorithm work on NDC and make sure it doesn't go beyond that is just further clip that bounding box to these NDC screen edges. So you just make sure not only do you bound everything to the triangle's range, but then further restrict it so that the box itself always stays on screen. So you just do a lot of min-max checks to make sure that the box is in the right place. Pretty easy, pretty straightforward. Yeah, this part is super easy. A lot easier than the lines we actually had to mathematically clip, right? So that was a bit more difficult for it to be efficient. But this is quite a bit more easy. Now, there are faster triangle drawing routines than the Better Brute. I think I'm pretty sure I showed you one on day 2. Day 3. I've showed you like my parametric one, and there's other ones out there, and they're can be quite a bit faster. But the good news is the same idea of just forcing the triangle routines to stay on the screen with doing min and max type stuff. They tend to fit well with these other triangle algorithms too. So they all are pretty easy and straightforward to make work for triangles. And remember this, sorry, I should take this back. I don't know why I was saying NDC. Yes, you can do this in NDC with the bounding box. But if you remember, when we did Brute was not done in NDC. I apologize. I've been stuck to it saying too much about NDC, right? But yeah, you could clip it in NDC, but the Better Brute we do in pixel space. That's why it's so easy. Remember, this is 0 to 0. This is width and height of their screen. And that's where we do the Better Brute calculations anyway. So this would be during rasterization. We can actually let the Better Brute function deal with the clipping in 2D, and we'll just do the more mathematically intensive part just in 3D. Yeah, sorry, that's what I was going for, and not NDC. Although, yeah, technically we could have a box in NDC, but it wouldn't help because the whole idea of building those boxes was to loop through pixels, and NDC is this floating point space, and we're not looping through pixels in that space, so that wouldn't make sense. Okay, that being said, if you really wanted to, and you want to not do this on a pixel level, you could do this in NDC, just like we did for the lines. You could do that too, whichever is more comfortable for you. I just personally think that doing a slightly cutting down a bounding box is far easier to do than clipping it completely mathematically in NDC. But you could certainly do that. I guess if you made things generic, made these functions generic enough that they worked on any plane, then you could maybe copy and paste or recall the functions or what have you. But like I said, I think the pixel method might be easier. All right, so yeah, I know this was quite a bit, but clipping is a very important part of any rasterizer. So let's move into some tips for doing this for lab. So this is kind of covering everything. So first things first, when we're doing perspective correct interpolation, first part of today's lesson, pixel shaders, keep in mind, are designed to accept already interpolated values. They're operating per pixel. So you don't want to adjust your pixel shader to deal with perspective correct interpolation. This is just something you do while rasterizing, like your line or your triangle. You are adjusting how the UVs, how the colors, how those results are interpolated. That is specifically attacking the interpolation itself, so it's perspective correct. So you shouldn't have to adjust your pixel shaders for that. However, you will want to adjust your pixel shaders when you're doing enhanced texture filtering, all right? Because remember, pixel shaders, that's where you're doing the bulk of your texturing. All right, not the bulk, that's where you are doing all of your texturing. So when it comes to doing mip mapping, when it comes to doing bilinear filtering or trilinear filtering or anisotropic or what have you, that is something you're going to do right there in your pixel shader. So that is, yeah, that keeps the code very clean. That doesn't require a huge amount of adjustment. Though, you will want to send in a Z value to your pixel shader now, because you're going to want to know, especially if you do the naive mip mapping, you need to know how deep that pixel is into the screen so you can choose the appropriate level of the texture. So that's something you have to keep in mind. Yeah, and you might have been yelling this at the screen as we were talking about clipping. You might say, I already have clipping. I have if greater than 0, if less than with. I have that. I'm done. Well, yeah, it's true. You have very, very slow 2D clipping if you have that. Extremely slow, and your frame rate will really suffer for that. So you never have that in production code, but it would work. There's a problem though, and that is that doesn't solve the negative Z value problem. So when you have the Z's go below the near plane and become negative, and they flip the X's and Y's, you're going to notice, and your 2D clipping is not going to solve that problem. So you have to do clipping that's at least on the near plane. That you have to. All right. Another suggestion, I think I had alluded to this earlier, but this is a very important recommendation, is I would have your clipping routines, whether they be line or triangle, but especially line, return result codes. So I had given you some suggestions. Return 0 if it's a hidden line, return 1 if the line is completely visible, return 2 if the line was cut, if you had to cut the line inside the function. And if you return these codes as to what happened to the line, it's going to really make doing the triangle part that much easier, because then you can just send in the triangle, the lines that make up your triangle, find out what happens to the different lines through the clip routines. And not only will you have clipped lines potentially that come out of the functions, you will know which lines were clipped and in what way. Or if they're hidden, or if they're in front of the screen. And then that will help you make the logical decisions necessary to split up the triangles, or to just return, or just to adjust them. So that is super valuable. These codes are super valuable to help you to compute the right logic of what to do with your triangles. Finally, and probably most importantly, the vertex shader can no longer apply the perspective divide. Because if you make your vertex shader do the perspective divide, well, now you've ruined your chance to do any clipping. In fact, when you start moving into doing 3D hardware, you'll notice that you'll be like, where's the perspective divide? It's not here, or I'm not supposed to do it here for some reason. Why is that? That's because the hardware is going to do clipping. And if the hardware is going to do clipping, just like you're going to do clipping, you need to do it, at least on the Z, in homogeneous projection space. That means pre-perspective divide. So keep that in mind. Does that mean you don't do it anymore? Of course not. Of course you're still going to do the perspective divide, but not until after you're done clipping along the near plane. Okay. I know that was a very long lecture. Thank you for bearing video. Thanks for bearing with me. So here's your reading assignments for next time. And next time we'll be delving into some last fun stuff, some surface shading. So we'll really get even more mileage out of our pixel shaders. But yeah, that takes care of the lesson today.